All right, we're back. Today's lesson is going to be a relatively quick lesson on what's called simplifying radicals. So you've been working a lot with Pythagorean's theorem, which requires you to find a missing side of a right triangle. But many times the missing side isn't a perfect square. When I'm saying a perfect square number, if I list out the counting numbers 1, 3, 5, 6, 7, 8, 9, 10, and then I square each of them individually, I'll get a second column. And the second column are what we refer to as perfect square numbers, in that if you were to take the square root of each of these numbers, you would get back a nice whole integer value back, a whole number back. Like 4 square root of 4 rather is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, and so on down the line. We call these perfect square numbers. They're nice, simple numbers to deal with, especially when you're taking the square root of anything. And they're common values that you should have memorized kind of in your head. They should just jump out to you as perfect square numbers. You're not going to memorize every single square number. 11 is a popular one that shows up a lot in math. 121. 12 squared does frequently at 144. 13 squared is a 169. Then it jumps kind of weird. It jumps to 15 squared, shows up a lot in math. That's 225. 20 squared is 400, and 25 squared is 625. So your list of commonly occurring perfect square numbers, these values here, and those show up a lot in math in terms of perfect square numbers. But like I was saying earlier, a lot of these values that we run into, especially in solving Pythagorean theorem problems, aren't perfect square numbers. In which case you'll see many times the directions will be simplify your radical. And radical is simply this symbol here. When we say the radical, it's just that sign, the square root sign basically. So for example, if you have the square root of 24, well 24 isn't a perfect square number, but we can simplify it, and what that means is if you think of the 24, it can be broken down into factors. 4 and 6, and then 4 is 2 and 2, and 2 and 3. Now because we're looking at perfect square numbers, we can rewrite 24 as 2 times 2 times 2 times 3. It's the same thing as 24. And because we're looking for square roots, we're looking for pairs of same factors. Pairs, meaning 2. So here's a pair of 2's. They can come outside the radical. They in a sense cancel out of the radical symbol. So there's a 2 on the outside, square root. There's no more pairs left of what factors remain. So there's a 6, and then that becomes your simplified answer. The square root of 24 simplifies to 2 square root 6. If we look at the square root of, let's say, 50, again we can think of 50 breaking up into 5 times 10, and then 5 is already broken up, then 10 is 5 times 2. So when we say square root of 50, it really is the square root of 5 times 5 times 2. And then again, we look for pairs. There's a pair of 5s that can come outside. So the 5 comes on the outside. And then there are no more pairs left. So we say 5 radical 2 is how you simplify the square root of 50. If we have the square root of 18, right? 18 can break up into 6 times 3. 3 is a prime number, so it can't break up anymore, but the 6 can be 2 times 3. So when we say the square root of 18, it's like saying 2 times 3 times 3. And so there's a pair of 3's here that comes out in front of the radical again, so the 3 kicks out in front, and square root of 2 is left over. And the reason we look at simplifying radicals is because we occasionally run into radical work that has radical 50 plus radical 18, right? And these are two problems that we just did previously. The square root of 50 simplifies down to 5 square root of 2, plus the square root of 18 simplifies down to 3 square roots of 2. And you think of radicals like you do variables, like terms that come together. So if you have 5x plus 3x, that gives you 8x simplified, like terms. There's 5x's plus 3x's add together to make 8x's. Well, here we have 5 square roots of 2's plus another 3 square roots of 2's give us 8 square roots of 2 simplified. Together, simplified answer. And it's the reason why we like to simplify radicals to get like terms to come together, especially in algebra. So when we simplify square roots, you're really breaking down the radicand, the stuff under the radical sign, we call it the radicand. It breaks up into prime factorization. So you break them down into prime numbers. The factors of 50, for example, or 5 times 5 times 2. Then you look for pairs that can come out. So if there's a pair of 5s, there's a 5 on the outside. And let's say, for example, we wanted to simplify the square root of 48. Square root of 48, again, we would say, well, 48 is the same thing as 12 times 4, and 4 is the same as 2 times 2. 12 breaks up to 4 times 3, and then this 4 breaks up to 2 times 2. So this one has a length of factors. Square root of 48 is the same thing as 2 times 2 times 3 times 2 times 2. And here's an example of which there are 2 pairs of 2, if you will. So, for example, here's one pair of 2. So there's going to be a 2 that kicks out in front there. Here's another pair of 2 that comes out in front. So there's another 2. So times 2. You always multiply in the front. These are all multiplications. So that went away and that went away. Only the 3's all by its lonesome to stay under the radical. And this simplifies to 2 times 2 is 4 square root of 3. Breaking it up into common factors, prime factors, and then you pull up pairs. Eventually, what you want to be able to do with prime factoring and simplifying square roots, let's take that square root of 48 example, is to be able to recognize perfect square numbers. And that's why at the very beginning we said that this list of perfect square numbers are important, because as math people, when we get further on to math, we just recognize numbers in specific patterns. We say, well, that's a perfect square number, that's an even number, that's an odd number, that's a prime number, etc. But if we recognize the type of number we're dealing with, it makes simplifying things a whole lot easier. For example, when I see 48, I immediately think, well, 48 is really the same thing as 16 times 3, right? So 16 times 3. And there's a rule in math that says if you take the square root of the product of two things, well, you can really break that up into the product of two individual radicals. You can take them individually. And then the square root of 16, well, that's 4, because that's a perfect square. Square root of 3 is not, and there's nothing else you can do to break it up because it's prime, so 4 radical 3, which is the same answer that we got breaking it up with prime factors. 4 radical 3 was what we got using this factor tree method. But if you can recognize values straight away, it's a whole lot easier. For example, square root of 50 that we did earlier is really 25 times 2. When you think of two numbers multiplied to make 50, that one of which happens to be a perfect square, well, 25 jumps out of the page. So the square root of 50 is really the square root of 25 times the square root of 2. And then square root of 25 is a perfect square, being 5. Square root of 2 is prime, so there's nothing you can do with it, which is your solution for that. It's like if we did the square root of 72, I immediately think the square root of 72 is 36 times 2. And that means it's the square root of 36 times the square root of 2. And therefore, the square root of 36 is 6. Square root of 2 is your final answer for that. And again, that just comes with experience of being able to recognize square numbers, why you want to memorize those relatively quickly. I hope that helps in understanding how to simplify radicals. We'll have some practice problems for you shortly.